Hello. Today we're going to do a little talk about modern memory management in C++. And by modern, I actually mean it's over 10 years old. The modern way of managing memory was introduced to C++ with C++11, so the 2011 version of C++ that pretty much in most places where you will be dealing with C++, you will probably have that. But to understand what problem this modern memory management is supposed to solve, we will take a short dip into how old memory management worked. And then we will continue from there. Yeah, and that's pretty much it. And to also make it clearer what's actually going on, and to show you a few of the problems that you will encounter in the modern memory management, we will also be building our own version of this modern memory management, which is mostly the way to manage memory using shared pointer and weak pointer. So let's get started. Let's create a little class and call it settings. So this is just a example class in which we somehow store settings for the application. I'm not going to write actual code to store something. It's just as an example. We also have the class document. And in the class document, that is a, like a Word document or something. So while we are not going to write a very complex application, just think of it like this application can open multiple documents, and there are global application-wide settings that affect these documents. So how you usually did memory management in the old days was you used a command named new and a command delete. So keep in mind, we have variables. We can just say int foo equals 15 and can keep some data in there. We can also make a global variable by just putting it at the top level outside of any function. So we can have a gfoo, for instance. That works as long as you have a fixed number of things, but it breaks down, for example, when you need multiple documents. I mean, you can keep a list of all your documents, but it's hard to reference them, and sometimes you have data that isn't actually global, that is just attached to something else. And so that is why, so these variables inside the main function are stack variables. So that means that this variable, like whenever you call the function main, you get storage for one int. But what if you want to create an object, like depending on information from a document, like you have 15 files in there or something? And that's what you use new for. So we'll just for now, we'll create a variable. This could be anywhere. And name it first document and create a new document in there. Now, so that you can see what's actually going on, we'll give this document a constructor. Can't even type. We'll give it a constructor and print document created. Or, yeah. So this will just print the address of this object, which, you know, you usually shouldn't do. But here it's just enough to let us see whether this object exists. And in the destructor, we'll do it like this. Actually, let's do it like this. So at least we get a whole English sentence. Alright, so we're creating and destroying documents, and we'll do the same for our settings so that we can see. So now we create a new document. Now, if you just run this, you will see that it created a document, but it was never freed. So since this is all the program does, the program terminates and your operating system cleans up for you. But at least on most modern systems, on an embedded system, you might actually have forever leaked that memory now. So the least we need to do is we need to get rid of this object again. And you do that by using delete. So let's run this. And you actually see object with this long number here. That's the address created. And document with this long number destroyed. Yes, it works. So that's how memory management generally works. And of course, we can do the same with multiple things. For example, we can create a new settings object and delete that as well. That works as well. Now, you know, this settings object, like we created and we really just want to give it to the document that gets loaded and forget about it. So what we will do is we'll give the document a settings variable and we'll pass it in. And of course we should clean up after us, which means here we should say delete settings so that the object is freed. And just because I'm paranoid, I'm going to set it to null pointer. This is not strictly needed, but what this does for you, let's maybe put that on multiple lines now. What this does for you is that it that if you have a pointer, if you use the pointer for document after it has been deleted by accident, then it will crash more readily and you see it more readily, because as soon as you access settings or call any method in documents that might be using settings, it will try to access the address null, which on most operating systems is deep in the startup code, in the operating system startup code. And so they've kind of, like most operating systems, just say if your application tries to write or read at location 0, it's probably a bug blow up. So that's why we use that as the default value, because it's never a valid address from our program. So if we run that, we're going to have an interesting problem. Why is this? We're having... Oh, right. No, we forgot. this is still a compile error. Of course, we have to pass our settings over. Oh, and let's make this explicit. Just to be especially correct, but okay, so we run it and now you see it blows up. Why is that? Well, if you see here, it says settings 2134 created, document 2132 created, settings 2134 destroyed, document 2132 destroyed, and then again it says settings 2134 destroyed. So this gets destroyed twice. And how could that be? Well, we give it to this object and we tell the document to delete it again. Okay, easy solution. We just won't delete it here. Not a big problem. So let's run that again. And now we actually get what we expected. We create a settings, we create a document with these settings. Then when the document gets destroyed, the first thing it does is free the settings, delete the settings, and then it prints out, hey, I'm being destroyed as well. So that works. And now you've already seen the problem we have. And that is, imagine you had two documents that use the same settings. Then each of these documents thinks, oh yeah, I don't need the settings anymore, so I delete it. But that means that if the first document deletes an object, then the second document doesn't have the object anymore, even though it needs it. And so we need to find a way to keep track of whether we still need an object. And so how do you do this? So the good old way to do this was something called reference counting. How you do is you create an instance variable. I'm initializing it to 1. You will see in a moment what that's for. And that is a counter that tells you how many objects are using this object. And then you add a method, retain. All that does is it adds 1 to the reference count. And then we add a method called release, and that goes subtract 1 from the reference count, and if that's 0, then let's put that on its own line again. And if that's 0, then delete this. And now we prohibit everyone from actually calling our destructor. And now you see we're getting an error message, which is here on the delete statement. That's intended, that's why we made it protected. Because instead of saying delete msettings, we now say msettings release. And now we need to do something else. So we have this counter now that tells us which object uses ours. So that means when the document gets this settings object, it should call settings retain to tell the operating system, okay, I'm keeping this around. And then it will balance its retain with a release. And that will, of course, happen in first document and in second document. To make this more obvious, let's add some more log messages. So cout retained settings all right, and released settings. So now we're going to get a log message whenever that happens. Now we have to do one more thing. So each of these will retain and release it for itself. So that's how these objects can say, I'm not just reading this object in here and then returning, I'm actually storing it and I'm interested in keeping it around, in not having it deleted yet. But so, of course, we create this here, and the main function also has an interest in this object staying around. You know, if, for example, we called delete first document up here, we would have a problem because if the count in settings when we create it was initialized to 0, you know, then of course this document would retain it, but when this this document gets released, it will release it again, and then this object will be gone. And that's why we say, okay, whoever does a new settings, of course, wants the object to stay around as well, so we'll start out with 1. But that means if you do a new on an object that is reference counted, or you do a retain on an object that is reference counted, you must call release on it. So that's what we'll do. We'll call settings release here. And we have these documents, and let's go back to actually creating 2 objects at once and deleting them one after the other. And now if we run this, it will look slightly different. So we'll see the settings gets created, the first documents gets created, and it retains the settings object. Then the second document is created and it retains the settings object as well. We should probably... You know what? Let's just run this in the debugger, I think. Well, let's first finish here. So, and then we're deleting the first document. So it says released settings once and destroyed the document. But you see, we haven't destroyed the settings yet. Then it says released settings again and destroyed the second document. Still, the settings are still around. And then we get to the last line, settings release, and that releases it a third time, and that's when our counter hits 0 and goes to destroyed. So we're managing this. But now let's do it differently. You know, we know the main function really only needs the settings object while it is setting up its 2 documents. So let's put the settings release up here and then do delete first document and second document. And then let's just run this in the debugger and watch what happens. All right, so we're in the main function. And here we can step into settings, and settings will initialize its reference count. So we have an object now, and you see the reference count is 1. Yes, that's nice. So let's step out of here, and we'll see in the console it says it has created the settings. Good. Now that we've created settings, you can actually see it here. The object settings has the reference count of 1. Now we create the document, so we step into that. It initializes its settings pointer to null. So you see here mSettings equals null. Then we do, we log that we've created the object, and we retain the settings. And now here in settings, you see that the reference count has actually gone up to 2. So it knows now that both the main function and this document still need this object to stay around. Then we also remember the settings in the instance variable. So that's the same object. If you look at the address, here it's written in hexadecimal, not in base 10 as our usual log message is, but you see it's 0101 6CAD8. It's exactly the same address. It's the same object, and both have the reference count 2. Now the constructor of the first document returns. The same thing happens in the second document. So if we step over this now, we should get this reference count going up to 3. And yep, it is 3. It remembers here mSettings with a reference count of 3. Nice. So we have all the objects we want now, and the object knows or remembers for us that both the main function who created it still wants it to stay around because it needs it, and our 2 documents, first document and second document, needed to stay around. That's 3 in total. And now the main function is done with it, but not yet with the documents. So it releases it, and you'll see the reference count went down to 2. So this is the point at which the main function should no longer use this settings variable. Now, if I had been paranoid enough, which I usually am, but wasn't here, I would have set the settings variable to null. That's an easy way to prevent yourself from doing something stupid like that. Because if you try to call a method on null, on most operating systems you get a reliable crash. As I mentioned, you're accessing address 0, which can only be operating system code. So let's now delete the first document. And of course here, first document has been freed. So this is all garbage data, as you see. It doesn't see the object anymore. But in second document, which still refers to settings, or even in settings itself, but that shouldn't be there, you can still see the reference count is 1. And now let's step into delete second document. Oops, that step into didn't work. But now settings is freed. Settings no longer exists. What I really wanted was I wanted to see the destructor. So let's just run this once more, just you can see it. This time just step over, we create a settings, we create the documents, we release mains hold on settings, we delete the first document. That of course releases the settings. And then we delete the second document, which also calls release on settings. And now here in release, you see the reference count is 1. So we print our log message, and then we subtract 1 from the reference count, and then check, is it 0? And yes, it is. So that means nobody is interested in this object staying around. So we can delete ourselves, which, be a little careful. Like, delete this is dangerous. If any line below this line still does something, like accesses the reference count or another instance variable, or tries to call a method on the object itself, that, of course, is forbidden. The object is already gone. But, your function is still running because you can't just stop a function. The function still has to return. So this will just lead to pain. If you're lucky, you get crashes. If you're unlucky, you overwrite some new object that has already been created or something, and then produce garbage, and your program will just behave weirdly, and you'll have no idea why. And it will behave weirdly, 5 minutes from now, the next time that memory that you damaged is used, not immediately. So these kinds of bugs are hard to track down. But this is how reference counting works. An object has a counter, and you count up and down, so multiple parts of your code can access a shared object, but that object's memory gets freed when everyone who needs to use it has also been freed. And I keep saying freed. Free is the old name, how one used to call delete in plain C. So excuse me, I should have said has been deleted. Okay, so we have reference counting here. And now you might already see the problem. If you look, C++ has existed since, I actually don't remember when it was created. I think it was in the 80s or something. It's pretty old. And the thing here is C++ 11. So that's like 30 years after, or something like that, a few decades after C++ originally came out. They added reference counting to it. So that means you have a lot of classes like settings that already exist and that do not have a reference count nor retain and release methods. And that in turn means you can't really, like if you just told everyone, add a retain and release method and a reference count to your struct, they couldn't use any old structs and some or classes. So any of their classes, first they'd have to go through and do this all by hand, and this is not actually thread safe, so making this counter and the delete thread safe would be extra work. Things like that, And so the decision was made, we want a non-intrusive solution. We want a solution that lets us attach a reference count to an object without changing the object. There's also a second problem. You always have to remember to call retain and release here explicitly. And so let's solve this problem first. How do you do this? Well, what they did was they created a class that they called shared pointer. I'll call it shared pointer uppercase. The real name is, shared pitter, really. And there was also, before that, was a class named auto pitter. What auto pitter did was basically it took a pointer as its parameter and called delete in its destructor. Why is that useful? Well, let's do it with shared pointer. We know we have to call retain to keep an object around and release to free it. Let's just make this specific. No, actually, let's make it a template right away. So we have the type of the object that should be shared. And now we say, okay, we have a pointer here. And this concept is basically called a smart pointer. Let's call this smart pointer so it's easier when I talk about shared pointer and our smart pointer class that we're now doing. But basically smart pointer is our homegrown version of shared pointer, just so you see what will be going on under the hood. So now we need a constructor. So smart pointer, that's a pointer to t. So and then we initialize the pointer to our object. And what of course we shouldn't forget is whoops, I don't get autocomplete here, of course. We have to retain it when it comes in. And when this is deleted, we'll call release on it. So what does this get you? Well, it means here, instead of saying settings pointer settings, we can just say smart pointer settings. And create this. Whoops. And here we use a smart pointer as well. Let's see, I think we'll move it all the way up just to be safe. And so now here we also say this takes a smart pointer settings. And that means we can just assign one to the other. And we don't need to release it anymore. And here we need to change the type as well. Let's just see, are we doing everything? We initialize it to null pointer, but we should also use null pointer here. All right, so what are you complaining about? Okay, it's unhappy because we're not, that's just a stylistic complaint. So since we're doing the assignment here, instead what we should be doing is just call the constructor here. It's basically the same, but it's bad style. Thank you, program, for reminding me. Also, we didn't have an assignment operator defined on the settings class, on the smart pointer class, so that's also another problem. We should probably do that. Operator equals t pointer object. And so what you have to do here, of course, I think this wants us to return self. So what we want to do here is, first, if we have a pointer, then we want to release the old pointer. And then we want to assign the incoming object to it and retain that as well. Now, here's one problem with this function, just to be overly correct. If you assign the same object to this smart pointer that is already in the smart pointer, this will release the object, possibly make it go away, and then use the dead object and call retain on it. So what we should actually do is we should reverse this. How do we do this? Well, we can do t-pointer old object equals mputter, and then do it like this. So now we've remembered the old object, then we... No, actually, we don't even need to do this. I'm stupid. What we just need to do is we say object retain, because we already have a variable with that object in it. So now its reference count is 1 up. We're guaranteed that it will stay around. Then we'll check mputter and release it, because that's going away now. And then we store the object, which we've already retained, in mputter. So that means if it was the same object, then the reference count just goes up by 1, then again down by 1. So we've done basically nothing. Whereas if it was 2 different objects, then it's just that we first retain the incoming object and then we release the outgoing object. We don't, you know, like, it's not like we free it and then replace it. You know, it's just a tiny delay. It doesn't matter. All right, but this means we have an operator equals as well if we need it, and it's a safe one if we assign the same value. All right, so we've done this, and we do not need to call settings release here. Now, why is that? Because smart pointer has a constructor and a destructor. So you can already see, like, if when a document is created, and this, then we call the constructor on mSettings, which, you know, retains this and stores it in the pointer in mSettings. So this is the same that we manually did in code, just hidden inside the smart pointer class. And when the document gets destructed, it also destructs all its instance variables, its properties, whatever you want to call them. And so that means tilde smart pointer gets called, which calls release. Where is it? Here, which calls release and sets it to null. And the same thing works here. At this point, this smart pointer gets created. Now, what happens then? Well, this is like a local variable. So it lives until the end of the main function. And here at the end of the main function, when the return is about to leave this function, it calls all the destructors. So it calls tilde smart pointer and releases this settings object. But now you may remember that we actually use to call release here. So how would we do this? Well, there are different options. One thing that you could do is you could give the smart pointer some way to tell it set yourself to null, which actually we can. We can just say settings equals null putter here. And that will not only, that will call the assignment operator we just defined, and will release the object and set the new object to null. Oh, and of course that shows me one mistake I made. Of course I have to check if there is an object at all, because if there's null incoming, then there's nothing to retain. All right, and now we should basically get the same printout as here, if I didn't do something stupid. So let's see. We create a settings object and it got retained. That shows our smart pointer works. Then we create the second document and then it says released settings. Yeah, that's the that's this call. I guess it's this release. I'm a bit confused here. Just to be safe that I didn't write anything wrong, let's log the reference count here. It should be here and here and here. And of course the editor is being too smart for its own good. All right. Let's try and run this again and see what happens. So we created it, we retained it, we created another document, and then we are releasing settings, which is at 2, and will then go down to 1. So I'm just missing the log message. Oh, right. Let's just avoid the confusion, and since it says retained and released, wait, wrong way around. Let's do the counting before we log. All right, sorry about that. So we create it, then after retaining it, it has the reference count 2. Then we create the second document. Oh, I know what I did it wrong. Okay, here's the problem. The parameter is a smart pointer as well. And we haven't written a copy constructor for smart pointer. So it just copies the pointer in here and doesn't count it up. So let's say here we need a smart pointer t. Should probably make that const. Copy the pointer over, and here we retain it as well. And that should fix that bug. Okay, so settings is created. Now it gets retained once. Oh, I think we still have one issue here. This new actually now needs to have a reference count of 0 to start out with. You know, because when we initialize this with an object, this will retain it anyway, and we want it to go away. So that's just a convention. You're not allowed to call release and retain by hand anymore, only through the smart pointer, and then everything is fine. But oops. Okay, what happened now? Okay, let's go through this. So settings was created. Of course, it now has a reference count of 0. It gets put into settings, which gives it a reference count of 1. Then we pass it to the document. And that is another smart pointer. So the copy constructor should now be called. That's why it gets retained. Then this one gets copied into M settings, so that's how we get up to 3. All right. But now we don't get any releases. Okay. I'm probably not a good programmer, because why is release not being called? Did I forget that? Here, this says mputter release. Oh, and I should probably go if mputter. Let's put that on its own line again. Okay. So we're handing in an object, assigning it to that variable. And again here, probably check if it's null. Just so we don't blow up. But why didn't this... We should be getting one release here from this smart pointer. So I'm a bit confused why this copying... Maybe just make sure that we're not compiling nonsense here. This one gets retained. And let's see if that copy constructor gets called at all. Yeah, it gets called. And that counts it up. And now... Yeah, that was the M settings. And, oh, document created, yes. And after that, did we get a release? Yeah, okay, here. I just misread it. Okay, so this, let's see how far it goes. Okay, so here is what happened. So we created the settings object. We assigned it to the lowercase settings local variable, which is a smart pointer, so it counts the reference count up by 1. Then we pass it into the document, and the parameter retains it as well. And then the parameter gets copied to the instance variable. So here, mSettings gets assigned lowercase settings. So that's why the reference count goes up to 3. Then we get the log message document created. So we've created our first document. And then this settings object gets released once. That is the parameter going out of scope. Now, we're doing the same with the second document. We already have it in the lowercase settings variable, so it's just passed to the document and the parameter retains it. And then it gets copied to the instance variable, mSettings, which also retains it. So we're up with 4. Then we log document created here. So that works as well. And then the parameter goes out of scope. So its destructor is called, and we go down from 4 to 3. And again, it's the same reference count that we had before. The settings variable and the two documents are holding on to settings, nobody else. Makes sense. Then we set the settings variable to null pointer, which calls the assignment operator that we defined here, which, you know, has no incoming object, so this code doesn't get run, and then releases this and sets mPrinter to null. So that is a release, and it goes down to 2 because only the documents hold on to it. And then we destroy the first document, and that destroys its mSettings instance variable, that one up here, together with the document. So that gets its destructor called and calls release, and we're at a reference count of 1. And then the second document gets destroyed, same thing. It destroys its smart pointer, and we get a reference count of 0. And at 0, of course, release triggers destruction of the settings. So now we have some nicer memory management, because it means we can just set up smart pointers like this anywhere, and they will automatically, when we assign a new value or clear them to null, release or retain our objects for us. So we always have the guarantee that this pointer stored inside this settings has correctly been retained for us. So far, so good. Now we have the problem that I mentioned, that you already have classes like settings that exist, that do something. Settings doesn't do anything because it's just our example. So we would like to not have to modify settings to have a reference count. So how do you do this? Well, the way it was done, since you know, nobody knows where this object came from. You know, it could have been created using new and delete. So someone else could have created it for you using new. So you have no control. You just have the pointer to something of the correct size. So what you do is you create a second object for the reference count. Let's just call this ref count. And here, and change all these to ref count as well. And now we make a new class, settings, pool is, I don't know, is it raining? Something like that. And now just so we can follow it a little better. Let's have it log settings, this and that created. I'll put a tab in front of it because we of course have the reference count separate, so you will always get the message from settings and the message from the reference count. And really, the message from settings is, you know, if you see they're both there, you don't really need to read them. So let's say deleted. Okay, so we have a settings object and we have a ref count object. And now we have to change smart pointer to use this ref count. And how we do this is just we create one when we get a pointer, because this is the constructor we use to assign the value returned from new to the smart pointer, right? So the smart pointer now has to remember both pointers. Ref count and the other one. So now, of course, in all, so we remember the object, but we call retain and release on mref count. And of course, we cannot have this assignment operator anymore because we can't just assign it a pointer. So we rename this and call it reset. And now we just say if we have a if we have a ref count, call release on it, and set computer to null pointer, and of course set the ref count to null pointer as well. And the copy constructor, of course, also has to copy over the ref count. So ref count object dot ref count. And so now we can retain the ref count. And here it just releases it. And we should probably do pointer equals null pointer. Okay, we've copied those two. And we need to create the ref count here. New ref count. All right. And since we know that the only spot these are created is here when we get a new object, we can now go back and say reference count is 1, and then we don't even have to call retain here. Starts out once retained. All right, so now the only problem we have right now is we do mref count release, and that doesn't actually delete the mputter. So the question is now, do we just, yeah, I think we'll just parameterize it. I'm not 100% sure. I think it's slightly off from what shared putter does, but it's the same principle, and the details aren't that important in this case. So now we have a t-pointer here, and we say if it hits 0, delete mputter as well. All right. And that, of course, means we need to initialize it as well. And we could probably even go and log for which object the ref count is created for. All right. And maybe use that here as well. All right, put it in here as well. All right, so this should be good, except, yeah, that we still need to create it correctly. So we now say ref count putter. So we're basically wrapping our object. Oops, that should be a pointer. All right, are you happy now? Oh, right. It needs to have the right type because it's parameterized. So now we have the ref count, and we actually don't even need the pointer. All right, so we can now initialize a new smart pointer with an object, which creates a separate object with a reference count for it. And when you copy a smart pointer, it also gets a pointer to the reference count and retains the reference count. So it's basically all the same thing as before, just that we've added the reference count object in between. And actually the reference count object is the object that gets managed via retain and release, and it has a pointer to the actual memory that on which it calls delete when it's time for it to go away. So it's not really very different. Oh, of course, I need to do that in the right order. And just to be paranoid again, since the object is going away in this line anyway, setting it to null here is not really needed, but that way you get a guaranteed crash if you ever access an old object that you've already released or something. So that's why we do this. Alright, so this should basically be the same. We're creating a new settings here, and here we need to change it to reset. I don't like the name reset, but that's what shared pitter, so the standard C++ class, calls it. So that's why I'm using the same name. So if you see it on shared pitter, you'll know, oh, that's the one that clears it out. So now we should be able to just run this, and if I did it right, not much should have changed. So let's see. We create the settings object. We create a ref count for this very same settings object. Then it gets retained, the document gets created, and the ref count goes back to 2, which makes sense because it's the settings locals variable and the first document. Then it retains the ref count 3, you know, and to 4, creates the document, it goes down to 3 again. That's the same as before, just that it happens to the ref count and not to the settings object. Then we reset the settings local variable, and so it goes down to 2. Then we destroy the first document, which causes our ref count to be released, which again is the same as before. And then we destroy the second document, the last owner of that ref count, and that releases the ref count, counts it down to 0, and at that moment it goes, okay, now I need to delete the settings, and after that, now in addition, the ref count gets destroyed. So yeah, that's basically how shared pointer works in C++, in the new class. So it's a very convenient thing because any memory that you have can just be handed to this and it will call delete on it. Even better, in shared pointer, you can actually specify a function to do the deleting. By default, it just calls delete, like our smart pointer does. So that would be, or like our ref count does. Here would just call delete, but it calls a function that calls delete, it gets the pointer. And so if you use some other memory management call, for example, a Windows specific one, or malloc from standard C because you're calling plain C APIs or something like that, then you can also use a shared pointer and just give it a function that calls the right call to free up this memory. So that's all nice and good, but now there is one problem that many people stumble over. So imagine settings. Maybe settings wants to talk to the operating system, and wants to register itself to be notified of changes to the settings file, so it can reload its settings and always be up to date. Now, the problem is, so the operating system also uses smart pointer. That's good. You know, the operating system will hold on to settings and send it its messages and won't crash. The problem now is, how do we get the smart pointer here? Or rather, the ref count. Because if you look at how the code flows, here we call new settings, so that runs through. And new settings, so we do not have a smart pointer at this point. We first need the pointer to settings, the dumb pointer, and in many cases that's the only thing we have. You know, we get that, but you know, in this case, settings actually knows about smart pointers, and so the problem is only when it gets assigned to the constructor of the settings variable. So when we end up here in this code, is the ref count actually created. So basically, before this line, we do not have a reference count yet. So we cannot give it anywhere. And yeah, that is just a fact of modern memory management in C++, is that shared pointer does not let you get a shared pointer to an object in its own constructor. There is no way to hand the ref count out of the constructor. You know, so even if you created a smart pointer here, you'd only shoot yourself in the foot. So if you do, you know, smart pointer settings this, you know, and do, I don't know, register for file changes, you'd have the problem that this creates a ref count. And only this one knows about this ref count. And when you go out, this one will create a second ref count. And then you'll have the same problem as before, because each of these is only one, even though you have two classes, two other objects referencing it. The file notification thing and this local settings variable. So if either of them is done, it will see, oh, it's gone down from 1 to 0, and will call delete, because it thinks it owns that memory. And then the other one, for example, so the other one will then still think the object exists, and when it gets done, we'll call delete on it and crash. Or even just if you try to call some method on it, will crash. So, and that's basically a problem. You cannot, you cannot do this. You must not do this in modern C++. If your object needs to give a smart pointer out after you create it, what do you do? Basically what you have to do is you have to create an extra function. So like you create a method named setup or init or something. And that does the registration once this whole thing exists. But now you may see, hey, I still can't do this. I only have this here. How do I get my ref count? And the solution to that is something called enable shared from this. And basically, I just realized I should have looked something up how it works in detail. So it's a base class that you can put, for example, in settings. So let's do a class enable smart pointer from this. And what this class basically does is it keeps a pointer to the ref count around. It actually keeps an entire smart pointer around in practice. But for our case, just keeping the ref count around is enough. And so let's just hand in a reference, then we don't get that extra copy. Oh no, we can't do that, right? Right, it doesn't have a constructor. So just let's give it a set method, and that's smart pointer t. All right, and here we say putter ref count, assign that to ref count. And now, whenever you need a this, what you do is enable smart pointer from this settings, and this also gets a method oh, we need, no wait, the ref count has a pointer, right? Shared smart from this, and that in standard C++ is called shared from this. And so that returns a smart pointer t, which it creates with mref count. And now I think we're missing that here. So ref count t pointer. And of course, this now has to retain the ref count, because this is always used for this copying over. So we have enable smart pointer from this, and this will create a new smart pointer pointing to the same object and already once retained, of course. And so now in this spot, we can just call smart from this. Now the nice thing here is, if you notice, we keep around the ref count, but we do not retain it here. This has several reasons. First, this enable smart pointer from this base class is the class of the settings object. So if we retained it, we'd have a circle in our retain. So that means, whenever the last reference to this object goes away, this object would always still have one reference to itself, which of course would keep it from ever being deleted. So we don't want this. And the difference between these two types of reference are called strong or weak references. And so a shared pointer, or in our case smart pointer, is always a strong reference. And a weak reference is a reference that doesn't increase the reference count, or at least doesn't keep the object from being deleted. Why this difference is important, I'll go into a moment. You can ignore it if it doesn't make sense for you. But anyway, so this means we can get a shared pointer to ourselves, which, this one lives as long as this function call, and then, although it's basically as long as you call setup, we retain settings, but then when register for file changes is done, our shared pointer here gets released again. Only if register for file changes keeps it around somewhere, then it keeps us alive. But that's fine, because that means it needs us. And we just need ourselves to stay alive long enough to register for the file changes. So that's not a problem. But yeah, so this is good. But now I've mentioned, so now you can, in any function, get a shared pointer to this object itself if you want it. So now, what do we do in other cases where we might want such a weak reference? Like, imagine you have an index. So you have a list of objects that are in another list, and they are keyed with certain keywords. But if someone deletes an object in the original other list, you do not want to have it still stay alive because it's still in the index. The index would give wrong results. Ideally, you would want the index to tell you at the latest when you try to access an object, oh, this object is no longer around. Well, so what you would do, what I'm not going to do today, is usually you would go into the ref count, which is a fairly small object, you know. It has a counter and a pointer. And you would put a second counter in there, a weak reference count. And now you call delete when the regular reference count, or let's call it the strong reference count, hits 0. But the weak reference count is what controls the lifetime of your ref count object. And so what you can do is you can have you can have a separate class like smart pointer called weak pointer, and that just does a retain weak or release weak, which only counts up the weak reference count. And that in turn means that whenever you, well, I guess let's write some dummy code. So weak pointer, this is funnily called weak putter in C++ as well. Again, it's templated. And basically, let's go, oops. Let's go here. If strong reference count and weak reference count is null, then we delete all of them. And now we make a second copy, weak retain and weak release, and that counts up or down the weak reference count. And again, if so, strong reference count equals null. That case will be covered up here already. Oops. So we don't actually have to delete the putter here. We can only get in here if both are 0. And if the strong reference count went to 0, delete has already been called. So down here, if the strong reference count is still 1 and the weak reference count is 0, there's nothing to do. And if the strong reference count is 0 and the weak reference count is 0, that means there are no reference left. So we just delete the ref count object. Totally makes sense so far. All right, and so we have the weak reference count now, and we have the weak pointer. And the weak pointer is basically the same as a smart pointer. All right, just that it calls the weak versions. All right, and here we never create a weak pointer from a plain object. Instead, we create weak pointers from smart pointers. Again, let's pass a reference here. We should probably do that down here as well to avoid having to constantly copy it here. All right. That will reduce the reference count by 1. The like these temporary dips will no longer be there. Okay. Oh, we should probably put weak pointer below smart pointer because one uses the other. All right, so this takes a weak pointer, a shared pointer, and now pointer ref count. We copy over that object, and then say ref count weak retain, of course, here as well, because this only had a strong retain. So that's slightly different. But now we can create a weak pointer for a smart pointer that only contains a weak reference. We can create one from a ref count. That's good as well. And we can copy one that retains. We actually don't need the ref count. Oh well, let's leave it there for now. Doesn't matter. And here we do a weak release and null that one. And yeah, I guess a reset method is okay as well. And what you also need is a lock method. So what does lock do? Again, that's a name I don't quite like. It's the method how you get a strong smart pointer again from a weak pointer. And so what do we do here? So first we check if ref count strong reference count is bigger 0, or rather equals 0, then we do smart pointer we just return an empty smart pointer. What we also do is we clean up. We call weak release here, because now that someone has asked us, is there an object inside you? We actually now know that there's no longer an object in us. So we can decrease our weak release count, and if our weak reference was the last reference to that object, our ref count will now also go away, not just the object the ref counts pointed to. All right. If we should also cover the case of if not mref count, then we just return an empty smart pointer. If mref count strong reference count is 0, then do a weak release and set ref count to null pointer, and then from then on we end up in this case and early exit every time. And now the last thing is, oh, the strong reference count is actually larger. Then we just do the same we did for the shared from this, which is we return a smart pointer for this ref count object that we have. All right. And that's basically how you implement a weak pointer. So a weak pointer just only reference counts this ref count object here. But if the strong reference count goes out of scope, then it has already deleted the object, and the only little bit of memory that's still left is this ref count object, which, you know, is only a few bytes, so isn't that big a problem. Yeah, basically, that's how shared pointers work and why you would want them. And there is, though, I've simplified this. There's one big thing that I completely glossed over. None of this code is thread safe. Remember multi-threading, where if you, for example, do foo plus equals 5, what your CPU actually does is it does something like x equals foo, x plus equals 5, foo equals x, where x is a register on your CPU, but foo is in your RAM. And so, since a computer breaks down everything into smaller instructions, you can't just add 5 to a variable and think that's one line of code that happens in one go. It doesn't. And so that means if two CPUs at the same time add 5, you know, so let's say you have, let's call this x2, do this, and maybe let's say move this a little bit. They're not quite at the same time, you know? They're like one started a little later. Then you have the problem that, so first, for example, this one runs and copies foo, which originally is 42. So it copies 42. Then it adds 5 to x, which makes x 47. And then this line runs. And it copies foo, which is still 42, to x2. And then it also adds 5 to it, so it's 47. At the same time, 47 gets written back to foo. So foo is now 47. And then this one goes and writes its 47 to foo as well. But remember, you added 5 twice, so the result you expected of plus 5 on the left side and plus 5 on the right side would be plus 10, so 52. So you've just lost 5 somewhere in between these two calls, because this one didn't get the result from this yet. So you have to somehow, in threading, make it so that this code gets to run completely before this CPU gets to access foo, to read it and write it. So well, we can actually leave this here, I guess. And now, where could that be a problem for us? Well, in our reference counts. So the strong reference count and the weak reference count, they need to be protected for threads. So that when you add to one of those, nobody else can at the same time try to add and gets forced to wait until that one add has happened, which, happens in a split second, but, at least the results don't get interleaved. And now the thing is, shared pointer in standard C++, its ref count class is thread safe. So if you call retain or release there, or weak retain or weak release, or their equivalents, because these are internal details, so you never get to see what they're called, and Microsoft's standard C++ library might call them something else than Apple's standard C++ library. So this one is protected for threading. So they use a lock, which is basically something like a Boolean, but it's not a Boolean. It's a special Boolean that is thread safe. So don't just put a bool here. And anyway, they use a lock to make it so that you can add to these variables from various threads at the same time, from different CPUs at the same time, and it will work. However, smart pointer and weak pointer are not, or rather, shared pitter and weak pitter are not thread safe in C++. What does that mean? It means you can have a smart pointer in an object as long as you only use this individual smart pointer from that thread. So that is that I'm actually not sure whether enable shared from this has a problem with that as well. It might. But anyway, it's nice explaining this stuff to you. I actually suddenly realize what I never really looked up. I'm sorry. But anyway, but what you can do is you can take a smart pointer, copy it into another object that you newly create, into a smart pointer variable in that object, and then take the second object and move it to a different thread, as long as only one thread accesses it at a time. That's fine. And then that other object can use this other smart pointer to access objects, or rather, this other shared pitter. Because they're different objects, so don't get in each other's ways, and the ref count that they share is thread safe. But that means basically if you have a smart pointer, a weak pointer, weak pitter actually in the standard, and a shared pitter in the standard, which is the equivalent to our smart pointer. But if you have one of those two, you have to treat them like any other variable when it comes to threading. You have to put a lock around them so that they can only be accessed by one CPU at a time. But you can keep these accesses short by creating a local variable, which is a smart pointer, copying your instance variable's smart pointer, which uses a lock, over into that local variable, then giving up the lock again, and so whoever else deals with this shared pointer in your object can now lock it, read it, unlock it. and you have your copy, which you can now use on your thread safely. That only applies to the pointer, of course. So remember that you still need to protect the actual object. So, for example, the settings object. If that's not thread safe, then using it through a shared pointer will not make it thread safe. You still have to do all the normal work. But it means as long as you copy your shared pointer to another thread and not just use the same shared pointer from 3 threads without a lock, it's thread safe, like a normal pointer variable. But since the documentation explicitly points out that the ref count island object there that we have, the one that we called ref count here, that is thread safe. Many people take that to say, oh, shared pointers are thread safe, and they're not. You still need to lock them. Anyway, this was a lot of talking, but I hope that all this code, even if in the end it didn't actually run anymore, was of use to you and helps you understand how shared pointers in C++ work. It's really nice that you can just do it like this. You could create a shared pointer, assign it a object that you newly create, and then, hand them off to other objects and use them there. And all the reference counting that happens under the hood is just taken care of by those. All you have to do is make sure you don't do any strong circles. So if you have an object that creates another object, and that other object needs to call back to the original object to tell it, I'm done, or something, then this other object must use a weak pointer to point back, and then it can just temporarily call lock on the weak pointer to get, it can just call lock on the weak pointer to temporarily get a strong pointer, call back, then the strong pointer goes out of scope again, but the weak pointer is still there if it still wants to call back. And so, yeah, that are basically the things to watch out for, and you spend a lot less time manually doing new and delete on objects. Now, there's one more little detail here that I should probably mention. As you may see, in cases like this, where we have this settings object that actually knows about smart pointers, because, for example, it has to be a subclass of smart from this, it would be really nice if we could avoid needing this extra ref count object. Because if you know a little bit about memory management, it's that your computer generally, if you ask it for, let's see, how large is the ref count? It's 4 things. These are 64-bit integers. This is a 64-bit address object pointer. So that means that's 8 bytes. 3 times 8 is 24 bytes is how large this object is. Probably another 8 bytes No, actually, that's it. Yeah, we have no virtual methods. So it's 24 bytes in size. Now, the thing is, the computer has to manage all this memory. So every time you say new a ref count object, it doesn't just give you 24 bytes, but rather it gives you a little more usually. Usually it's something like, so you can't get, for example, 2 bytes. Usually you get 16 or 32 or something like that, because it just splits the memory up into little chunks. That way the management information, like where does this memory block start and how long is it? It needs to know that to be able to reuse that memory later when you say delete this. And so, there is, I don't know, 16 bytes just to remember that this pointer exists in this spot and is this long. Blah, blah, is this long. And so that means if you ask for 24 bytes and it needs 16 more, so that's 40 bytes, then it probably gives you a block of 48 bytes in addition to however large settings is. And settings, when it gets allocated, has the same problem. It's, here it's a bool. So let's assume that's 1 byte. It will probably blow that up to 16. And then it will go and add another 16 in front of that for the managing operation, or somewhere in a table of contents or whatever. So you get 32 bytes plus 48 bytes would be 76 bytes for a settings object that is really, so it seems a bit wasteful. And so one thing that you can do is there is a function called make shared. And so let's create our own make smart version. Template class T. It is a little smarter because it can deal with parameters, but we'll just do the void version for now. And so what this does is it basically internally, like, it has to do this in a different way, but I'll do it in a readable way. Basically defines a struct that starts with a ref count. So that is the object that we have up here. But it's not a pointer to that object. And then it continues with the actual object. And so what it does is, let's call this combined, and then it basically does a new combined, and here is where our implementation breaks down. Remember, I originally said it contained 2 pointers, 1 pointer to the object and 1 to the ref count. Basically, that's what this does. So it will return a, that should of course be T, but in our case it would be settings. So smart pointer T, And what it does is it gives it the new combined ref count, ref count, the address of that as the first pointer, and the new combined object, a pointer to that, as a second pointer, and stores them separately. So every time you say, I want to actually access the object, it will give you that second pointer. And when you do anything reference counting, it will go through the first pointer. Or I guess in our case, we could also do this by just saying here in the new combined ref count and then what did we name the variable? Mputter. Equals new combined I guess we could actually do it this way and not need the 2 pointers. Whatever works, it's fine. Okay, so this is probably a better example. So you'll have so basically it does this. It creates a new combined data structure that contains in one memory block, and thus with only 16 instead of 32 bytes overhead, it will create your object and the reference count. And then we'll tell the smart pointer that's your reference count, and it will somehow tell the smart pointer do not call delete on this. Because, of course, this is a pointer inside the combined thing. You have to delete the entire combined thing. You cannot delete one variable inside it. But anyway, so that's roughly how it works. And what make shared, as it's called, does for you. So in general, if you want to create an object, you don't do new and then create a smart pointer. You just do make shared or make smart to save yourself the overhead of the extra housekeeping information and allow the computer to pack the data a little more closely together in that data structure. Of course, there might still be some alignment stuff in there, but it's a little more efficient. Of course, that also means if you do make shared, if you do use make shared, and you have a weak reference to your object, then it will not free the memory of the object. It will actually call the destructor and free all the objects that you're... So if the settings object, contains a hash map of all the settings from name to value, then it will actually call the destructor and clear the entire hash map, but the actual settings object's memory will still be there until the last weak reference is gone. But that's, a lot less. Usually you have big object trees, and so freeing most of the tree, or the entire tree even, if there are no weak references, will, free enough memory for what you need. And then the weak references will soon go away as well, taking those few extra bytes away as well. But yeah, it sounds scarier than it is. The only reason I'm mentioning this is if you go into your program and debug it, and at a certain point say, okay, my settings object has been freed. Now I should have the exact amount of memory I had before I created the settings object, for instance. And then you find, no, wait, there is actually, there are, like 24 bytes less available than I expect. That's why it is. Don't worry about it. Those will go away eventually. But yeah, that's basically all I can tell you about shared pointers and smart pointers in C++. You may notice that we haven't actually used a single one of them. So let's just comment all of this. No, actually, let's not. Let's not use the shared pointers and things. Yeah, basically check out these. So make shared, all of these are in the standard namespace. So that would be standard make shared and standard enable shared from this, and standard weak pointer pitter, and standard shared pitter. Those are kind of the main things you want to use. Oh, right. I just remembered. There's one little detail. So you may know that, you have a ref count to document, or a ref count for document and a ref count for settings or something. Doesn't really matter. But they're class specific. So what if you have subclasses? You cannot you can't really typecast them. Usually what you would do is, if you had a subclass of document, so say a class picture document, then of course, did I write something wrong? Oh, it's probably because this one doesn't compile. Anyway, oh, it's probably, oh, I don't know. Probably some syntax error, something that it indents wrong right now. But so you have a class like this. But now you have a smart pointer document. And usually if you have a document pointer that actually contains a picture document, like here, what you can just do is you can typecast picture document, second document, and then, call a method on it. And the C++ compiler will make sure that it actually calls the picture document method. If it's a picture if it's really a picture document. If you did this with first document, of course, you'd get some sort of interesting crash. Or rather, what you would do in C++ probably would be static cast picture document. That's what you would do. Like this. So fine. Or you could use dynamic cast, which will test. So if you do, you can do something like if dynamic cast picture document first document not null pointer, then you actually know it's a picture document. And you could, if you kept this pointer around afterwards, so like, you know, something like that, then you could do that only if whatever document you have in a document variable actually worked. If it actually is the type you expect. This is, of course, bad object-oriented style, but in some cases you need to unpack an object because the base class gives you the pointer and the base class doesn't know that it's actually a subclass. But of course, usually you would have a method in the base class that you just call, and then if it's a plain document, it does one thing, and if it's a picture document, it does something else. You know, that's always how object-oriented coding should work. Now, how do you do this if you have a smart pointer to a document? Well, with smart pointer, we haven't implemented it, but with shared pointer, if it was one like this, so make shared picture document. So if you had this one and now wanted to call it, you cannot static cast it. That's because, and you cannot just, you know, do, you know, initialize a shared pointer picture document with this. You can't just do pick one to do it the same way as here, as above. I mean, you can't just do something like this, because these are completely different, unrelated objects, and the computer doesn't know that they are, so you have to cast them. And for that purpose, there is a method like dynamic cast and like static cast, or rather there are two methods. So you could use static pointer cast, and this will now, of course, again, this is like static cast, and if you call a method on this one, and it's not actually a picture document, you will crash. And then there is also dynamic pointer cast, which gives you null back, or rather a shared pointer containing a null pointer if it's not the right type. So you can just go if pick one not null pointer, then so that's the last thing to keep in mind. Never use normal typecasts on shared pointers or weak pointers. Always use the dynamic pointer cast or static pointer cast versions instead. And that's basically all I can say. I hope it's been useful in some way, but and I also know that it's very in depth what I did here. So usually, if you use shared pointers, you will not have to worry about most of this. Like, how often do you actually need to downcast a class or something, or upcast? I don't know. Depends on where how your trees grow. And I mean, what you need to know is you need to know about shared from this. In case you want to point a pointer to yourself, pass a pointer to the object itself to someone else. From inside the object, you have to know that you must not use shared from this inside the object itself. So settings in the object's constructor. I mentioned that earlier. And also, by the way, you will get a weird error if you try that. If you call shared from this here, when you create a new object with enable shared from this, whoops, yeah, no, it's here. At some point, magically for you, this set call will be made so that it knows about itself. I think it's when the shared pointer gets your object, it will call this. So in the here, where it creates the new ref count, that will also figure out if the object is with enable shared from this, then you get a different version. Something like that. So yeah. And so that means the ref count pointer in our case here, the pointer to the object itself, will not have been initialized inside the constructor and will be null. Now, if you call shared from this, you will actually get an error message when you pass that pointer elsewhere, because shared from this checks if you have a so smart from this in our case, the official implementation actually checks if it has a ref count and terminates your program if you, or throws an exception, I think it is, bad weak pointer or something like that, if it hasn't been initialized yet. However, there's a second version. There is smart from this and there is weak from this. Shared from this and weak from this in the official enable shared from this class. If you use weak from this, it doesn't do this check. And so if you use that in your constructor, you will not actually see that it's wrong until later when you go like, oh, my object has gone away, but my object already still exists. Why is this pointer that I handed out in the constructor already invalid? So that's something you will have to watch out for. Definitely just don't use shared pointers in constructors. Ideally add like a setup method or something that you call after the constructor. One thing I like to do is I have this pattern where I have a create method that returns a shared pointer. So in this case, that would be smart pointer, but shared pointer in your case. Would be like this, create. And then here, of course, it takes all the same parameters that the settings constructor does. And then I'll just do auto settings equals make shared settings. This is, of course, now it makes sense for you, right? It's a static method, so it exists without the object. And I call make shared to create the object. I return settings, and I call settings. I call a method like the setup method on this one. This doesn't work here because I haven't actually implemented being able to get the object out. So I would have to do ref count putter. Shared pointer actually wait, setup is gone now. So here. This is what I would call. In actual shared pointer usage, you can actually call settings direct on it, but because it has an override for the arrow operator that gives the object on the inside. But anyway, so I have this method, and then I can just, people see this method and go, okay, I always call this, and then those two steps will be done for me, and I get my shared pointer back. Bingo. And from then on, I just use it normally. There is one problem with this, and that's that usually you would go and say, hey, I don't want anyone to call the constructor. Let me just make this protected. Or even private. But the problem then is that make shared cannot call the settings constructor. As you see, calling a protected constructor of class settings declared protected here. So in this case, you sadly have to make it public. Only public, so make shared can call it. Alternately, of course, you could just go and say shared putter settings and new settings here. That would work as well. But then again, you pay for the extra housekeeping information. It's a trade-off, but then this can stay protected. Because the one who creates your object, allocates it, is actually your own method, and that, of course, has access to private methods. But anyway, that's really it now. I think I've covered everything I could think of. But yeah, now, never use shared pointers to the object being constructed in its constructor. Second, smart pointers, shared pointers, need their own lock, just like any other variable if you use multithreading. Use weak pointers if you create and own a strong reference to an object that then has to call you back. So it should only keep a weak pointer and call lock on it as needed to get the strong shared pointer out of it. Use enable shared from this in everything except an object's constructor to get a shared pointer for this in the moments that you need it. Um, and use make shared in classes when you create them instead of creating a shared pointer and then using new to create the object. And that way you'll avoid some overhead. And never typecast using dynamic cast or static cast on a shared pointer. Instead, use dynamic pointer cast or static pointer cast. That's the C++ memory management rules. But the cool thing is that means you can just allocate memory dynamically on the heap, and C++ will clean it up for you. So for example, if I crash, I return from this function. Okay, this is the main function, so returning from it means your application quits. On modern Unixes and things like that, that means the memory is cleaned up anyway, but assume it was some other function inside your application. If I returned at this point, say an error occurs, an exception is thrown, and I just exit this function, this object gets its destructor called. So the settings object gets deleted, just as you wanted to. But these two, they're just in stupid normal pointer variables. They get leaked. Now, of course, I just said this object gets freed. Since we handed this object to these two documents, you actually get, they actually still retain this object, and since they are leaked, so is that object. But I mean, if these objects weren't released, the old approach to memory management would leak these objects, but smart pointers don't leak them. You could solve this issue through use of the old auto pointer class. Don't use auto pointer. It does a lot of things wrong. Instead, use unique pointer if you only have one reference to an object. This will not do the entire reference counting hoo-ha. This will just do delete when this variable goes out of scope. But, you know, in many cases, the shared pointers are actually... Unique pointer is if you have a function that needs to allocate a buffer of a dynamic size to do its work in, and then once the work is done, that pointer needs to be freed again. Or that pointer then gets returned as the result, but still only one person will use it and look at it, you know. And shared pointer solves the whole problem of multiple parts of your code, not people, actually parts in your code, need to deal with this object with different lifetimes. And now we're really done. I hope you enjoyed it. There's some other movies like this on my YouTube channel about making your own programming languages. So if you're curious, look at that. And the other clips on this channel. Thank you, and bye-bye.